This will be scientific revolution. You've all heard about it. Here's some interesting facts about it.
Hey, Maddie, you want to record this so you can post it on the. Oh, there you go.
Okay. Transition in human philosophy from philosophy to empiricism. Philosophy isn't as concrete as science is today. There weren't any special, things like the speed of light is constant and the laws of motion and go on and on. This occurred during the 16th and 17th century in the European countries. There's a lot of evidence to say that some of this was discovered by other cultures earlier. The Chinese was certainly one, and there were some others. But there was no communication between the various ones at that point, and so the information didn't get passed on. Okay, it's a shifting of how you think about it, rather than some particular event. And many scientific societies, and the first one that moved into the realm of what we would call science was alchemy became chemistry. And it was not a fast transition. It slowly moved from one to the other as people started to investigate some of the things that the alchemists had seen but couldn't explain. Atoms, I'm not going to go through this. You've all seen atoms more times than I can count. Periodic table is based on the atomic number, atomic mass. Those are the numbers you normally see. The 6 up there on his back of his t-shirt is what?
The atomic number.
Atomic number. Exactly. And the other is the atomic mass, 12.0107, I believe. Yeah. When you see this, it's measured in AMU, which stands for atomic mass unit. These are so small and have so little mass that they had to come up with a different scale. Otherwise, there'd be too many zeros. Isotopes are the atoms of the same element but have different masses. And here's the information about carbon-14. Carbon-14 is very rare. It's only 1%, 0.1% of all the carbon on Earth is carbon-14. But that 1.1% has allowed us to date things in many cases. Sometimes things are too old for it, and it's not useful for something that's happened in the last 10 years or anything, but it has helped to date many archaeological finds. And I talked about weighted averages. You remember weighted averages takes into account what percentage of each of the isotopes is commonly found in nature. Mass number. Protons and neutrons are basically the same. Electrons are tiny. In a tiny world, this is really tiny. 1 over 1837 AMUs. And most of the time, when we do calculations, we ignore the mass of the electron because it's so small. Mass number is the sum of protons and neutrons. Okay, ions and atomic charges. When you start changing these particles, things change about the atom. If I change a proton into a neutron, now I have a different substance because I've taken one proton out of the nucleus. Maybe it's still there, but it's a neutron now. And so instead of it having a mass of 6, it's got a mass of 5. That type of thing. You change the number of neutrons, you've got different isotopes. That's the 12 and the 13 and the 14 for carbon. And if you put, somehow change the number of electrons, you get ions. I don't know if they'll ask you this, because this is one thing I sometimes have trouble remembering. Positive ions are called cations, and negative ions are called anions. There's the mass number, the atomic number, element symbol, how I normally put mass over atomic number. Weighted averages we've already talked about. This is a little bit of information about it, but it said the same things we said before. Mass spectrometers. This is something we didn't talk about in the past. A mass spectrometer, as the name says, is using the mass of an object to figure out things. What they're showing there is you've got some kind of source down here. These are just a few of the names that it could be. And as it goes up, because there's a large magnet here, and these particles bend a different amount depending on what they are. And so you can see they're separated out. Separate isotopes out, and you can find out what element you've got. You can find out what isotopes it's made out of, which is important in some cases. And it can be very helpful in determining what a compound is. And so they make it seem so easy and so fast on TV shows. It's not nearly that easy, not nearly that fast, but it can be used to identify unknown substances in many cases. These things down here are called Faraday connectors, and they then send information to some kind of input device where it's recording the values as they are found. What is this stuff made out of? The first thought was it was earth, wind, fire, and water. That seems funny to us today. But think about this. You're born. You bleed. What do we know that's the same kind of consistency? Water. You're warmer than the surroundings. What is there that we know is warm? Fire. When you talk or sneeze or something like that, you're exhaling, and that's wind. And finally, when you die, you turn back into the earth. And literally, that's some of the idea they came up with, and then started applying it to everything that was around. You can see the logic. It's wrong, but you can see the logic. Okay, where the atom comes from Democritus and this guy. Democritus was important for a number of reasons. His name will come up again. And you notice now, this is the first time that we start to move into science, because what he postulated was that these particles that he was finding, atoms, were indivisible. Again, he was wrong, but he was close to being, knowing what was going on. Modern atomic theory changes everything. Started out in the 19th century, was when it first was formulated and publicized, and it has continued to be modified as more information has become available. We call these small particles atoms. Atoms are a given element. Atoms of an element are not changed by chemical reactions. Chemical reactions work on what we call the valence electrons, which are the electrons in the outermost shell. They don't involve the nucleus. They don't, if you have a substance that has multiple layers of electrons, the different levels, 1s2 and 2s2 and all of that, it's only the outermost that take part in chemical reactions. And most chemical reactions are tending towards getting the elements back to a point where they're completely stable and don't react, meaning that that outside ring is full. They're still called valence electrons, but that ring is full, and when it's full, it's much more stable. All of the inert gases, that's true. The outside orbital is full.
Halogens.
They, in the early atomic modes, couldn't explain this at all. And this was something that people pondered over a lot at one point. How could this be true? And this was, they saw the change in colors of metals when they were heated to high temperatures. And their model of the atom didn't provide any help to them about what was going on. And some people started to understand that there was more to it. They didn't know what, but there was more to it. Okay. When you look at hydrogen and you spread it out, the light coming from it, you spread it out into a spectrum, you'll only find that there are 4 lines, each pertaining to a particular color, and each indicating a jump that an electron has made from one orbital to another. And so this is a way that you can determine exactly what the metal elements are, exactly what something is made of, if you can get it to the elemental state. The Bohr model. Niels Bohr, he worked on this problem of those lines and what they meant. And he caused a significant change in the atomic theory, because he came up with the idea of these orbitals. And he postulated that an electron had to be in one of those 3 orbitals for particular, well, one of the orbitals for any particular element. And that the colors of light were caused when an electron, and we call it an excited state, meaning it's got more energy than it normally does. When it drops back, it has less energy, but that energy had to go someplace. You can't create it or destroy it, and so it comes out as light. And that's where those lines come from. And if everything is in as low a level as it possibly can be, it's called the ground state. If you don't know it, this is what Albert Einstein won his Nobel Prize for. Not for what we think of today, the general theory of relativity and those kind of things, but he won it for this. Why? Because the theory of relativity was much too debated at the time. There was a large group of scientists who thought that he was entirely wrong, and others who thought he was entirely right, and they argued a lot. He explained a lot more of what was going on, and at the time, he explained something called the photoelectric effect, which is the basis for, in your garage, you know, if you walk through, the door might go, if the door is going up, it might stop, or reverse directions. You're experiencing the photoelectric effect because there's a sender on one side and a receiver on the other, quite close to the floor, and a beam of light goes across. It's hard to see. But when you interrupt that beam of light, it sends that fact to the garage door opener, and depending on where the garage door is, it will either do nothing or make adjustments to the position.
Isn't that what like people use on like home security or like safes?
Yeah, it's used that.
Safes. Not doing.
We have a number of feral cats in our neighborhood, and they keep wanting to get into the garage. It's warmer, I guess, and that kind of thing. And I know when they're there because I'll lower the garage door, and the noise makes them run, and they run right through that beam, and that garage door stops and starts going back up. So it is exactly that. It can be used for intrusion detection. You know, where the garage door is actually supposed to be a security device so it doesn't come down and hit you in the head. Okay. You have light, it has to have a certain amount of energy. It hits this plate right there, and that causes electrons to be emitted. The energy came from this light, and it was enough energy that the electrons actually were completely released from the element or the nucleus that they had been bound by. And okay, they're measuring it down here. Okay. There are problems with that model. The Bohr model, they realized had problems. One of those problems was that they found out that there was a difference between hydrogen and other elements. And that is, in hydrogen, all the electrons were of a certain energy were in the same orbital. Well, that's not true when you go to other elements. It's more like the average energy instead of the energy. And that didn't fit into the model. Here's why. Electron repulsions, the charges push each other just like two magnets will either be attracted or they'll push each other away. And so they had to come up with a more advanced model. And that's where we got the 1, 2, 3, 4 and SPDF, which is still, has been modified greatly, but is still used. Here's an attempt to show you something that's actually three-dimensional in 2 dimensions. These are some of the various shapes that they believe occur with electrons going around the nucleus. This, what it means is the different colors indicate the frequency, how much of time does it spend in that level and that amount of energy. You see that on all of them. And they're showing you what happens as you go down. From here to here, this is basically 2 dimensions. When you get to here, you get 3-dimensional. So it's not only going up and down, it's going on the plane directly out of the board. Clover shape, I just don't see the orange slice shape that they say F orbitals are in. And there's a summary of it all. Pretty straightforward. If you've had chemistry, this is old stuff.
Next year.
If you haven't, yeah.
Honest chemistry.
Yeah. Periodic table. The periodic table is organized in a very, very systematic way. Everything in these 2 groups, or in these 2 columns, has 1 electron if they're here, 2 electrons if they're there in the outermost shell. Then we move to this transition area where we start to get additional layers, and we find out how they work. And then we get over here where things are going to become very stable again. They don't start out that way, but when you get over to here, these are the inert gases, and they're extremely stable. It's very difficult to make them react in a chemical reaction type way. And then along came these down here. They found the original periodic table didn't have this. They found that they were finding elements that didn't fit the pattern neatly until they postulated that there were another layer of orbitals. And so they put it this way, just to try to keep things together in a logical fashion. Questions? Okay. The number in front of the A over there tells the number of valence electrons. And the A's are over there and over here. In the middle, doesn't follow the pattern as well. This is a question, this table is something I like to ask questions about. And the question is, if I go down a column, what's going to happen to the energy?
It increases.
It depends on what layer you're talking about.
The energy, are you talking about the ionization energy?
Because it would be ionization energy, yes.
It goes like this.
Mhm.
Goes diagonal, left, right, down, up.
This is what happens to the size, the atomic size. Why is that happening? Why are they getting smaller when they're adding more neutrons and protons?
Because the charge in the center is becoming higher, which attracts the electrons on the outside more, which
Pulls it in.
Yeah, which will pull it in, squish it down more, and less volume.
And so you get,
More mass, less volume.
right, you get over here, and these are the ones that are inert again. And going down this, the atomic size increases. So going down the columns, it increases. Going across the rows, it decreases. Ionization energy. Ionization energy is the amount of energy it takes for this electron to be removed. And so the very reactive elements have low ionization energies. And the elements that don't want to react at all have very high ionization energies. I did that once before. In every case, we're looking at valence electrons with that, just the outer shell. Electron affinity. This is a time when energy is released, or if you want the opposite direction, would be needed. The energy released when an electron is added to an atom's valence shell. As we add electrons to that outermost shell, it is likely to become more reactive until that outermost shell gets full, and then it's the exact opposite. Electronegativity is the pull that this atom has on electrons. Here's the explanation of that. The nucleus can get closer to the outside of the electron, resulting in higher electron affinity and electronegativity. When we get to the larger elements, it's the opposite. We're only going to go with this for a little bit more. Okay, low ionization energy. Okay, reactivity. This is a measure of how reactive a substance is. It means that a chemical reaction is going to occur. That chemical reaction may be very mild, and it could be explosive. If you take a tiny piece of sodium and drop it into water, it will produce hydrogen gas. There's a good chance that the gas will ignite and give you a nice little explosion and all of that because of its reactivity. Okay, we're going to stop there and I'll take this up another time.